Hi, I'm Human and I do human-robot interaction. Today, with Annika Milbrad, Dan Safer, and Sean Andrus, we present you Reform, an algorithm to detect formations. This work is done as a collaboration with Atlas Institute at University of Colorado Boulder and Microsoft Research and AI. There are three contributions in this paper. First, we introduce Reform, an algorithm for detecting formations. Given a scene of people, Reform recognizes distinct conversational groups. Second, we introduce newly captured dataset Babble. Babble consists of a 35 minutes recording of conversational interaction between 7 individuals. This dataset is publicly available. Third, we introduce symmetry and tightness as two metrics to characterize formations. Detecting formations is easy for us and almost hard-coded in our brains. Here is an exercise for you. If I show you a scene of people like this and ask you select people who are in the conversational group, you can easily do that. Let's give it a try. Ready? Probably you came up with the same answer as I did. We have a formation of size 8 and a formation of size 4, size 3, size 2, and this is all. For sake of completeness, an formation arises whenever two or more people sustain a spatial and orientational relationship in which the space between them is one to which they have equal, direct, and exclusive access. Formations can appear in different arrangements. In general, formations that have more than two people tend to appear in a circular arrangement. When we have a formation of size 2, there can appear in 3 different arrangements: L arrangement, vis-a-vis arrangement, and side-by-side arrangement. Each of these arrangements can give us information about the activity happening in the formation. As an example, L arrangement happens when two people are collaborating or sharing a resource like a map, or side-by-side arrangement happens if two people are staring at a same resource like a picture on the wall. Now the question is how a formation is going to be useful in the field of robotics. In Microsoft Research, there is a robot named Direction Robot, which helps visitors to find places inside the building. It's necessary for the robot to know who are engaged in a conversational with it. We don't want the robot starts conversation with someone who is just passing by or a curious visitor who is just checking out the robot. This is not an easy problem to solve. Based on the sensor input to the robot, how the robot should decide the two gentlemen are part of the conversation and the lady in the back is not. What features should robot take into consideration? Is it going to be distance? Is it going to be angle or movement? What's the best way to detect formations? Many disciplines try to answer this question, although most of studies on formations done by social science community, in recent years there are a trend of using formations in the robotic fields, such as Marinel's work, or in the HCI community, such as Nicola's work. Many of previous approaches for detecting formations are limited due to reliance on threshold values determined heuristically using trial and error methods, and tuned for specific datasets. For example, the GraphCut algorithm uses a different threshold for a value named stride across various datasets to boost the accuracy of the algorithm. To reduce the need of hand-tuning parameters, our algorithm takes a data-driven approach to detect formations. Reform has 3 steps. Given a scene of people, first, the algorithm breaks the scene up into pairwise data points, capturing all possible combination of 2 individuals. Next, it uses feature-based classification to identify which data points constitute a conversational group. We use 2 features to train our classifier. The first one is distance. Distance is commonly used in a formation detection algorithm and is defined as the Euclidean distance between two individuals. This is an intuitive measure because people commonly converse with others in close proximity. In addition to distance, we introduce a new metric called effort angle. Effort angle defines how much body rotation would be required for two people to face each other with their body directly pointed at one another. Here is an example. For the left couple, the effort angle is going to be 20 degrees, and for the right couple is going to be sum of two numbers, 160 plus 120. So the effort angle is going to be 280. Last, the algorithm reconstructs the pairwise data into sets using voting scheme. So if the input to the algorithm is going to be these four people, the output of the algorithm is going to be highlighted people. Among all publicly available information datasets, we chose the SALSA dataset for training the model because it has a relatively large number of annotated frames and a large number of people in each frame. First, we divided the SALSA into 60% training set and 40% testing set. After we trained reform on the training set, we tested the performance of our algorithm on the remaining 40% of the SALSA dataset and also across two other datasets, HRI proof of concept datasets and Babble Dataset. Reform outperformed state-of-the-art algorithms across all datasets. For more results, please see the paper. Our second contribution is Babble Dataset. We observed that the most of existing datasets for studying formations have inconsistencies in the position and orientation. In most of these datasets, positions and orientations are manually annotated and are not prone to errors. To solve this problem, we use Vicon motion capture cameras and attach markers to participants to precisely record head and body positions and orientations. Babble consists of a 35 minutes recording of conversational interaction between 7 individuals. It boasts a large range of conversational groups of different sizes and arrangement, and it's publicly available at the link below. Our last contribution is to introduce two metrics to characterize formations. Currently, there are no metrics other than size to describe formations. The size of a group, however, may be insufficient to detecting important difference in formations. For example, formations can be constrained by physical objects like a table, limited by available space like a crowded bar, or altered by the context like presenter and audience, all of which can impact the shape and pattern of the formation. We define tightness as the average Euclidean distance between group members and the center of the conversational group. We observe that the tightness of a conversational group decreases as the size of group increases. Each two adjacent people in an formation create an angle with the center of the formation. Let's call this angle as adjacent angle. In a perfect symmetric formation of size n, all adjacent angles are 360 over n degrees. As an example, for a perfect symmetric formation of size 4, all adjacent angles are 90 degrees. We define symmetry of an formation as the average of absolute difference of all adjacent angles and the adjacent angle in a perfect symmetric formation of the same size. The symmetry for a perfect symmetric formation is 0, and as this number increases, it shows the formation is less symmetric. As an example, the symmetry value for this formation is 30. We observe that unconstrained conversational groups exhibit a high degree of symmetry and tend to be circular in shape. With that said, I'm going to conclude my presentation here. Thank you so much for watching my presentation, and if you have any question, please email me. Thank you.